diffusion constant by more than 1 order of magnitude. And using controlled polymer crystallization, we were able to create an energy gradient in space. A few references shown here. This is, as said, only the first part, the P3HD crystallization. That's something we're just preparing for publication at the moment. It's still unpublished. Yeah, and with that, I would like to acknowledge people and funding, of course. So on the left, this is my former group in Bayreuth. Some of you might even know Carlos Melo. He did a joint PhD between Bayreuth and Cali. He was in my group for a year. And on the right, a few people from Groningen, my new group, also contributed. Mainly here, Sebastian Städter. He did the shish kebab work. And finally, I should show this slide for our top master program in nanoscience. So if some of you know excellent bachelor students, please make them aware of this program. This is very selective, but it's very intensive, but prepares students very well for PhD in nanoscience and physics. Deadline would be 1st of February next year for non-EU students. So if you know a student, please put them in contact with me. There are also fellowships available to cover living costs and tuition fees. Yeah, thank you very much for your attention.
Okay, Richard, thank you very much for that very nice and interesting talk. Now we open the space for questions. So, las personas que se sientan más cómodas preguntando en español, Richard puede tomar las preguntas en español y responderá en inglés. Por favor, preguntas.
Yeah. Do you hear me?
Yes, perfectly.
Okay. Okay. Thank you, Richard, for this nice talk. That was really interesting. So yeah, it's more curiosity. I'm not an expert, so I would like just to make 2 questions quite general. So the first one is about this H aggregate and G aggregate. How do you guarantee you don't have a situation that is something between? I mean, I might miss that, but yeah, I guess it's because of the growing method or something, but you always have this perfect alignment, or you can have a situation?
Yeah, this is a very important question, actually. So we know actually that we have this perfect alignment. So first of all, if we go to this set of slides, if you remember, so we did electron diffraction on this electron microscopy images here.
Yep.
And from that, we know we have this nice stacking with a pi stacking distance of 0.33 nanometers. Right. So that is this distance between these orange cores of the molecule. So that gives us the first indication. And the second one is something that I did not show in this talk. If I go back to this slide here, if you remember, we have these hydrogen bonding amide groups here, these green ones.
Yeah.
And these hydrogen bonds, they are relatively strong, and we have 3 of those, and they really lock into position. So they really keep the core on top of each other. And we do have a molecule, and we're looking at that right now, where we have exactly the same molecule. So this orange part here, but without these hydrogen bonding groups, and they form J aggregates. So they stack in this fashion. They stack like this in a tilted and shifted, or a slipped stack, it's called, arrangement. And that is actually going towards a J aggregate already.
Okay. Okay. Okay, thank you. And then the second question that I have is about the simulations. I just noted something about the absorption simulation that in lower than 400 nanometer, it doesn't really fit when I see the emission is quite good. What is the reason of that? I mean,
so you're referring to that part,
yeah,
correct?
to this tail, yeah.
Yeah. This is related to higher excited states.
Okay.
So we are only excluding ground state and excited state. So the S0 and S1 of each monomer, and then the interaction. But of course, these organic molecules, they also have higher lying excited states.
Yeah, okay, so
etc. And in the monomer absorption, you already see it here a bit coming in, right? And of course, interaction also takes place in these higher excited states. And then, some features in the absorption appear, which is not grasped by our simple model. Okay, yeah, okay, I guess that also, but I just wanted to know is this bit, that's the reason. Okay, thank you so much. This was truly nice to know about this, and yeah, it's really interesting topic, and I'm happy that I could make it because I told John I might be not possible, but yeah, okay, thank you.
Thank you. Very good, David, very nice. Another question, please. Well, I don't know, nobody's asking. And Richard, I also would like to ask you about this, exactly this, this slide here. When you refer to the previous molecule that you implemented, you mentioned that you wanted to see the emission and you wanted to control the emission, exactly those ends. You mentioned in the first part that there was a mixture of coherent and incoherent transport, right? Yeah. But you wanted to make sure that what was going on inside the actual units. So in the second case, where you change the molecule and you control in a better manner the single nanofibers versus the stack bundles, for the transport of that energy, you have an energy landscape there that I found quite. I'm actually very surprised to see that fits quite nicely in a very lengthy positioning around from the left to the right in position that in the graphic you have in the center. So what can we know about this? When we change the strategy, you have the graph E and the graph F. For the energy transport, what would you, let's say, would you like to have for the control of that energy in transport? I mean, because in the bottom you have quite a messy structure, but you say that. So could you please mention something about it?
Yeah, that's actually a tricky question. I mean, on the one hand, is that what we have, let's start like this. We have actually a conflict with our measurement approach. So we use confocal microscopes. So we work with diffraction limited excitation of like 200 nanometer diameter. So we can only measure energy transport if it exceeds 200 nanometer or so. So in that sense, what we would like to do is clearly the first option here, where we have this delocalization because we know it's more efficient for transport.
Right.
Right. So we have longer range transport. It's more efficient. It's faster and over longer distances.
Okay.
However, the point is that actually this disordered energy landscape within bundles provides much more options to control where actually excitation energy goes. So assume hypothetically, let me just get rid of this scribbling. So suppose that you would be able to excite, say, this monomer, right? You could imagine to find a way that it goes left or that the energy goes right.
Okay.
right? That is something, then you can choose whether the exciton goes left or right.
Right.
But of course, the distances that we are talking about in this case, these are a few nanometers only. Yeah, this is the position of each molecule. So this distance is sub-nanometer. That's nothing we can resolve.
Yeah.
So on the one hand, this would be ideal to find a way to tune the directionality, whether we go right or left with energy transport. But the problem is it's probably not possible to measure this.
Mm-hmm. I see. So there's a dilemma between control and messy.
Yeah, it's it's a conflict of interest in this case.
Exactly. Yeah, of course, I asked the question thinking of having somehow control the internal units you might have in this nanofiber. And for quantum control, I'm thinking in that direction. So yeah. In the better organized structure, you have like a sort of less efficient energy transport. And yes, compared to the situation where you have this more messy situation. That's quite interesting, right?
But I mean, for
sort of collective effect rather than individual coupling within the fiber, the single nanofiber.
But in terms of quantum information, I mean, I guess the top structure is quite interesting, because here you have immediately entangled state of 6, 7, 8, 10 molecules.
Yeah, exactly. That's what I'm thinking.
An entangled state.
Exactly, but then you don't have control in the sense of that of an efficient energy transport within this structure, right? So it will be like a trade-off between those two situations.
Yeah, well, in the top one, we have good energy transport.
Right.
The top one is the better one.
Okay.
So the idea is essentially that if you have already, so if for example, this exciton here, wait, let me just delete it again. So if you have this situation here, and you are the molecule or the exciton would be delocalized over these two yellow molecules only, then it can make one hop downhill to these two molecules, right? But this would correspond only to 1 nanometer, one jump. In this situation on top here, we have a delocalization over 6 or so, and a jump to the next one here, where we have again a relatively smooth landscape and delocalization. This is then 6 times the pi stacking distance already in the center of mass, which would be, I think, like 2-3 nanometers already.
Okay.
You have to perform many more jumps, incoherent jumps, if you have a localized exciton than if you have a delocalized exciton. Then you make one jump, and you move the center of mass of your exciton quite a huge part along the fiber. So you need much less incoherent jumps. That's why it's more efficient. Okay.
So in the end, this could be useful then for quantum control, this sort of a structure you have here. Right. And how about controlling the phase? If you want to prepare pulses and if you want to prepare states, what happens in that situation in case E?
Yeah, indeed, that would be very interesting. Yes. Yeah.
Okay. Okay. I think there is another question. Someone asked here. Was it William?
Yes. Hi, Richard. First of all, I want to thank for that presentation. It was very interesting. I have a kind of question. I don't know if maybe it's like a little bit outside place, but when you show us the space-time diffusion process, that one, it seems very much like a Lieb-Robertson light cone for information propagation. I don't know if maybe you know that's about some works that do that have related those concepts with the works of you, of maybe you can tell a little bit more. the question I make it because it's pretty similar to a Lieb Robertson bond from a disordered system, and it's interesting that that appears here in this in this setup.
So the question was,
if you have seen some works, or maybe in your group have talking about that special form of the spatial temporal profile in maybe contrast with the Lieb Robertson bond.
Yeah, it's there is not so much other work done, in fact, at least not in this direct way that we measure it, right? That we really see in time and in space how this energy propagates, and then at least not on these nanosecond time scales. There's actually not so much work done. Plus, the other thing is that there are not many systems available that you can control in the way that we can control them, that you essentially can tune the degree of disorder in the system.
Okay.
Without changing anything else. So we have the same molecule, self-assembly is the same, but we change, well, of course, we go from a single fiber to a bundle, but the nanofibers themselves are the same, right? And that we can control disorder in this way, that's actually, as far as I know, the first time in this type of soft matter that has been done.
Okay, thanks.
There is another question, please. Omar?
Yes, thank you very much, Richard. It's a nice talk. I'm interested about to know what is the behavior of such aggregators when you use a different kind of excitation, for example, that two-photon excitation. What's happening with the transport in these aggregates?
Different kind of excitation.
Yes, so for example,
different wavelengths or pulse excitation?
No different wavelengths, yeah, different wavelengths, but in this case, using not one photon excitation, but two photon excitation. For example, using 800 nanometers in field pulse with 800 nanometers to excite the 400 nanometers level. What happens in those cases?
So the excitation that we use here, well, first of all, we made our life relatively simple and excited here in this range 450 nanometer directly into the main absorption, right? But in fact, what we did is we used, but we didn't do that on single objects. We indeed used 900 nanometer excitation to do some two-photon experiments, two-photon coherent control experiments. That really works. We don't really understand the results, but it looks interesting. Let's put it this way. I don't dare to show it yet, but it looks interesting. So it works. So you can use a two-photon excitation, but as said, it's not that we did this type of experiments with different excitation conditions. Yeah.
Yes. Thank you.
I don't know if we have any more questions. If not, I would like to ask another question.
I have one.
Okay, Mateo, go ahead.
Thanks. Well, first of all, hello, Richard. Thanks for the talk. A very interesting topic. My question is, for me, it was not clear if it is well understand the principle, the fundamental principle of the diffusion or the excitation diffusion in this kind of nanostructure. It is a model for this diffusion. It is well understand the physical principle of this diffusion.
Well, I would say half-half. When we first published this 4 micrometer transport distance in the first system here that I showed, let's see when it comes here, these examples. There was these 4 micrometer transport that we observed. Many theoreticians were actually very skeptical, and there was a paper out saying that this is not possible at all because our theory cannot explain it. So in that sense, it was not really understood, but we think that based on the this new measurements that we made here on this new system, so comparing these two effects, where we have in the single fibers with a smooth energy landscape with a large delocalization of excitons, and the bundles of nanofibers where we have this disorder-induced localization, where this energy transport is suppressed, that this gives a good hint for theoreticians actually to get or to improve their models to describe energy transport. And we have a group here in Groningen, a theory group, that comes now relatively close to the diffusion constants that we measure, in fact. So they are very close to reproducing our numbers that we have here.
Okay, because that's very interesting. I was wondering if one can propose like a kind of a stochastic model to model this kind of propagation of the diffusion. It's of course not a typical diffusion, but I was wondering if we can propose that kind of system or that kind of model. Sorry.
So I mean, of course, if you have any ideas, that would be great, because I said the models are getting closer to what we measure, but not really. So the models of our collaborators here, they do still not fully get to this 1 square centimeter per second diffusion constant. Yeah. So if you have any ideas, that would be great to improve modeling.
That's a very large value, right?
Thank you.
Yeah.
There is a very large value, right? The diffusion constant.
This one, the 0.05. This one here.
The top one.
This is 1 square centimeter per second. So this is the largest value that we measure, or one of the largest. And this is something that is not reproduced yet by theory. The bottom one for the bundles, this 0.05, that is something that theory can actually reproduce.
Yeah, I see.
Yeah.
Okay. Regarding the second part of your talk, those structures that you presented, regarding the energy transport, what would you like to see, or what works better for your interests? Or what are you thinking about you can do with the first sort of nanostructures and the other ones that you showed, the shish kebab sort of nanostructure?
Well, of course, we tried similar experiments as shown here on this slide, right? So in this case, what you would do is you would have your shish at this position, and then the P3HT nanofibers would go along this one, and like this. And then we have the energy gradient in this direction. So what we would actually expect is that we have preferential energy transport only in this direction, but not in this direction.
I see.
Yeah. So you really have the driving force away from the shish. Unfortunately, P3HT is a very bad energy transporting system.
Okay.
Yeah. So it really, we tried, but it doesn't really show significant energy transport.
Okay.
Yeah.
Okay, I see. I don't know if we have another question. I think we are quite lucky to have 18 participants yet, because it's lunchtime over here, Richard. You're already preparing for dinner, but here people are ready for lunch. So I would like to thank you for this
Welcome.
very nice talk. This colloquium, of course, you are a friend of CVOFI. You have collaborated with us in the past and continue to do so. And we are very glad to have you here. So
Yeah,
I wish
it was
you
a
all
pleasure.
the best of lucks with these structures and with all the things that I foresee that you might be thinking about for quantum controlling this sort of supramolecular structures and nanostructures. So thank you very much for attending this colloquium. This is the first colloquium we have had in the second part of seminars and colloquium at CVOFI. I think we will have one last seminar next week, and then we will be done for this year. And next year we will resume again and start again with the seminars. So again, thank you very much, and have a nice dinner.
Thanks.
Bye.
Yeah, it was a pleasure being here.
Thank you. Bye-bye.
Thank you very much. I think we can stop recording now, William.
So how is